and the spatial inhomogeneity. Spatial heterogeneity. That is to say, if the space is not homogeneous, what happens? And the interesting thing is, of course, that I want to emphasize the interaction in between. So to motivate that, I thought maybe I would start with the homogeneous environment, homogeneous equation, autonomous equation. I do want to say one thing, that is, before I get started, that is, I know people sit back there. I can only write so large, and as time goes on, I will write smaller and smaller. I don't mean to say that I would do that on purpose, but if that happens, please speak up. Everything I will be talking about will be very simple. So the simplicity is the spirit of my lectures here. I only do simple things. I don't do anything complicated. And I hope they're interesting anyway. They're simple, but I hope they're interesting anyway. So maybe I will now start with the homogeneous case to motivate why we are going to talk about the inhomogeneous case. All right. So again, I will start with single equation, but mainly I will move into, so that my second lecture will be mainly on single equations, but that's necessary as the background for us to go into the systems. So mainly I will talk about the systems for the rest of the lectures, but next lecture will be on single equations. So let me start with single equations. Okay. So autonomous single equation. Let's say we have a UT. Normally my notation is, when I talk about single equations, I will use lowercase u, lowercase v. When I talk about systems, I will use capitalized letters. Ut is Laplacian u plus, let's say, a diffusion coefficient v plus f of u in omega cross 0 t. Capital T can be infinity, and then we use Neumann boundary conditions. We always talk about Neumann boundary conditions. If I don't specify the boundary conditions, that means Neumann. And this is a parabolic equation, so we're going to talk about the inertial value, u0 x in omega. Let me just say, back there, can you see this? Can you see this? Okay, good. Way back, I don't even care. Okay. I know you can't, but there, if you can see that, that's good. So this is what I'm going to talk about. Omega will always be a bounded smooth domain. Omega. Bounded smooth in Rn. Always. And we always talk about Neumann. That means we have a normal derivative, normal, nu, outer normal, unit outer normal. And this one means d nu. This simply means dd, normal derivative. So this basically says there's no flux coming out of the domain or going into the domain. No flux across the boundary. Okay, so you see that there's no x dependence here. There's no x dependence. Just u. There's no x dependence. All right? So that's, so for equation like, for problem like this, when omega is convex, it was proved that if you have a steady state, non-trivial steady state, u, which is non-trivial, then it cannot be stable. So if omega is convex, then a stable steady state, I will use SS to represent steady state from now on. Steady state, SS. A stable steady state must be trivial. Trivial means constant. If domain is convex. This is proved. It's quite surprising. It's not so early. This is 1978 by Kasten and Holland. The paper is in JDE. So I need to explain a few things. First, what is this? I think everybody knows what a steady state is. A steady state means if U is a steady state, that means, let's say if V is a steady state, that means I have Laplacian V plus f of V equals 0, and V satisfies the boundary condition. That's a steady state. Okay? V, a steady state, is stable means what? It simply means if U0 is close to V, if U0 is close to V, this means close, then the solution U is close to V for all time. This means stability. Stability of V. So if the initial value is close to V, then the solution stays close. If this is true for any initial value close to V, solution stays close, that means V is stable. So Kasten and Holland theorem basically says that if you have a stable solution, steady state, that must be constant. That is to say, nothing interesting can happen if omega is convex. A problem like this does not support any stable, non-trivial pattern, non-trivial steady state. So, of course, later there are work talk about what happens if omega is non-convex. For instance, down the shaped domain, then this is no longer true. But anyway, I'm not going to touch upon that. So given this result, yes?
Were there any condition on F or for general?
Yes. It's a good question. First of all, what I said over there holds true for any diffusion rate D, number one. Number two, that holds for any smooth F. No conditions. Essentially, F just, let's say Lipschitz. Smooth. Smooth is enough. So if you have a peculiar one, then I'm not sure. But smooth definitely is enough. So it's a fairly general theory. But this is not how reality goes, right? We want to use reaction-diffusion to support non-trivial patterns, to model non-trivial phenomena, to model interesting phenomena. Then the theorem says you have to move beyond that. Either we go to systems, or we go to non-homogeneous equations, non-autonomous equations. That is, equations depends on x. All right. So maybe I spend a few minutes to talk about the system just a little bit to make connections with some of the interest here anyway. For systems, there is a famous example due to Dirac and Meinhardt. This is in 1972. What they did was that these are two theoretical biologists. They followed the idea of Alan Turing on an activator-inhibitor type of system, using activator-inhibitor type of system to model the head formation of Hydra. This is about perhaps it's one of the earliest example in morphogenesis. The head formation phenomena in morphogenesis was discovered by Tremblay in 1744. I want to describe just a little bit about the background of this one, and then write down the system, and then make connections to what people do these days. All right. A typical experiment that people do now in biology about Hydra is that, let me draw up. When we use Blackboard, we have some advantage. We go slowly. When we use PowerPoint, we can present pictures, nice pictures, realistic pictures. So today, I'm just doing it this way, so I cannot present nice pictures of Hydra. Anyway, schematically, let's say we have a Hydra of this kind. This is the head. This is the body. So one of the typical things they do is they take tissue out of Hydra near its head, the existing head, and transplant that to another Hydra. Then interesting things could happen. If you don't wait at all, do the transplantation, nothing happens. You take out a small section here, right? If you wait 48 hours, a new head and a new foot will grow. If you just wait 6 hours and do the transplantation, something very interesting can happen. If the transplantation site is close to the existing head, nothing happens. If that is far, then a new head will grow out of here. So this has led Turing to use the activator-inhibitor system to model such a phenomena. Basically, Turing is assuming that in this Hydra there are two chemicals. One is called the activator, the other one is the inhibitor. Activators activates both activator and inhibitor. Inhibitor suppresses both activator and the inhibitor. So the equation they wrote down is the following. Ut equals d1. The equation that Dirac and Meinhardt wrote down was the following. Martin u minus u to the p over v to the q. Well, let me just write down some examples. U squared over v, and then vt equals v2, Laplacian v minus v, this is plus u squared. And then we have Neumann boundary. On the boundary. And the basic assumption here that Turing argued in 1952 was that D1 is much smaller than D2. And when this happens, Turing argued the solution, you get one steady, at least you get one steady state, that'll look like the following. So this is supposed to be the body of the hydra. Then U will look like this, while V will look like this. V is nearly a constant, and U has a striking peak near one end of the hydra. And of course, this has led people, mathematicians, to do lots of work. And nowadays, we call the shape of this kind of thing U as a spike, or a spike layer. And people also found out that the equation, the single equation relates, because V is roughly a constant. So if you view this one as a constant, this equation will look like D1 UT, D1 Laplacian U minus U plus little u squared over a constant. Let's scale the constant out. It looks like this. So it's a Neumann problem. And of course, you have the mu equals 0 on the boundary. And it turns out that the domain geometry, omega here, plays an important role in determining where the peak is located. This goes hand in hand with the nonlinear Schrodinger equations. Well, nonlinear Schrodinger equations in the entire space, of course, there's no domain geometry anymore, but if you add a non-homogeneous potential, then the potential will create similar effect to the domain geometry. And there you also have spikes. You also have all kinds of things. And people have been working on that. Many people have been working on that. And I think in Korea, for instance, Professor Dion and his group also worked on that. And they have obtained many, many results. So this is one direction you go into a system following Turing. You see, I'm not giving any credit after that because the mathematics here is so tremendous that difficult to say anything in 2 hours, not to say 5 minutes. But today, here, we are not going to do that. Today, here, or in this school, we're going to do something simpler than that. We're going to move into the spatial heterogeneity direction. So let me now get started on this one. The model I will be using is particularly simple, particularly elementary. I will start with the logistic equation. Okay, so I will start here. The logistic equation looks like this. Let's say we have a population. We have a species in some domain, and we denote the total population by U. You know, the Malthus model gives us AU, right? That says U has to grow exponentially and so on and so forth. People say that's not quite realistic after a while, right? So later we have this logistic equation. U again is the total population. This is total population. then U satisfies the following ODE. This is ODE. UT equals U times A minus U. So this says, basically, you see, if U is bigger than A is a constant, positive constant. If U is bigger than A, this is going to be negative. The rate is negative, so U is decreasing. If U is smaller than A, U is increasing. But so we all know this is undergraduate ODE, sophomore ODE, second year. So the solution U goes to A. In other words, U identically A is a steady state, and the steady state is globally asymptotically stable. Not just locally stable, but globally asymptotically stable. So this is a globally asymptotically stable steady state. No matter what your initial value is, as long as it is positive, it converges to this one. Because the total population is positive, so we're not going to deal with negative initial value. So that's why I say with this A is, the steady state A is globally asymptotically stable. And A is a name. From the model, we say A is the carrying capacity. Sorry, I'm not writing it down correctly. Carrying capacity. In other words, A reflects the domain or the habitat capacity. It cannot support more population than A. Given a habitat, there's always a limit, right? And A means that it's the carrying capacity of the domain. The habitat, the domain, can at most support the species of total population A. So far it's very trivial. So what happens when you put in the diffusion? So we have UT, so Cauchy. At this time, all right, I put in E, plus U times A minus U. And we have Neumann boundary again. And initial value Ux0 is U0x. This is in omega. A is a constant. A is still the carrying capacity. The carrying capacity now is A times the measure of omega. Right. So this is the carrying capacity. This is the total, the limit for the upper bound for the total population. It cannot exceed this one when you add diffusion. You can prove this rigorously. So this can be proved. So this is a fact. U identically A is a globally asymptotically stable steady state. And of course, it's unique. Again, I'm talking about positive initial value, or non-negative initial value, and non-zero, non-negative, non-zero initial value. Any U0, as long as it's non-negative and non-zero, it converges to A. Any initial value, so we can converge to A. You can prove this one easily. I will prove something a little more complicated than this one next time. But anyway, it's very simple.
Asymptotically stable means it's stable near infinity.
T goes to infinity. So this means, thank you, Ux0, U0. If I write the solution in this form, sorry, Uxt, I should dot t. If I write this one as the u dot t, this means x. That's a solution depending on u0, right? This one converges to A as t goes to infinity for any inertial value u0. Any means non-zero, non-negative. Any inertial value. So this means it's globally asymptotically stable. All right. I will erase this now. So what happens if the domain is inhomogeneous? So let's look at that. Yeah, please ask if I'm not making any sense. As I grow older, this is how I always say. I say A, I write down B, and I meant C. It happens more and more often, and sometimes I just ignore something altogether.
Is it true for any t and for any omega? Is it true
This one holds for any omega.
any t? Any t?
Any omega, any t. For all omega, omega is bounded smooth. And for all t, positive. This is true. Now our story begins. Spatial heterogeneity. So in math ecology, of course, this is very simple, but not every point in the space, in the habitat, will have the similar carrying capacity. Yes?
So what if you have a derivative term like the mean effect?
You mean there's a gradient term?
Yeah.
Yeah. So the story will be a little different, but we'll get to that in the last. Actually, today I will talk about it a little bit. It'll be a little more complicated, but anyway, you'll see. Okay, so here's the. So suppose now our domain, our habitat, depends on x, right? U times, instead of A, we say mx minus u in omega plus 0 t. Actually, in this lecture, t is always infinity. I mean, I always write 0 t because sometimes people argue there's some finite time blow up, then you just use t. But here, everything, the time doesn't matter because we're talking about something very simple. So the solution exists always for all time. This is u equals 0 on the boundary. I just write it here. And then I have inertial value ux0 u0x. Here, mx, I will assume not constant. And I will assume it's non-negative. Again, it's a carrying capacity. At each point, it's a carrying capacity. So this is what we can do. This is what we will prove next time, theorem. If I call this problem star, then star has a unique steady state, positive steady state, which is globally asymptotically stable. asymptotically stable means the same thing, as I said before. We'll prove this next time. And I will denote the solution by theta, the steady state by theta b. It took me a while to get used to this notation, but this is people use in their area. So we're going to use that because you will see some advantage of using this theta b. So you look at this theorem, you say, there's nothing new. Yes, there's nothing new. Okay. Now, let's take this theta d and do something about it. I will do it here. So theta d satisfies what? Satisfies d, Laplacian theta d plus theta d times m minus theta d equals 0. Neumann boundary. Theta d is positive. So assuming I have the theorem already, assuming we have that, I want to do something about the theta d. I divide through by theta d. I will get d, Laplacian theta d over theta d. If theta d is positive, I can always divide it, right? Plus mx minus theta d equals 0. Now I integrate. Omega. Do integration by parts. This one gives me d omega gradient theta d squared over theta d squared. When I throw one derivative to the other, to 1 over theta d, so that maybe this is kind of important, interesting, so I will do it a little more. One more step. So this is the same as what? D 1 over theta d, Laplacian theta d, right? I throw one derivative over here. I have negative d, gradient 1 over theta d, well, I apologize for that. And then I have, say, gradient theta d. When I differentiate this, I get another negative sign. So what I'm getting is d integral theta d, gradient theta d squared over theta d squared. So what do we have? We have this term plus this one equals 0. But this term is positive because gradient theta d can never be 0. I mean, can never be identically 0. Why? Because if gradient theta d is identically 0, means theta d is a constant. If theta d is a constant, this is 0, this is a constant, m is not a constant, this is a constant. Equation can never be satisfied. So this is strictly positive. If this is strictly positive, yes?
So it means the theta d is bounded?
When I say this is a unique positive steady state, means the theta d here satisfies this equation and the boundary condition. It's a classical solution. So theta d is at least C2 omega bar closure. Okay. So this is positive. So that means these two terms add up negative. What does that mean? That means integral m is less than integral theta d. So let me write it down, what it means. Integral m is less than integral theta d. All right. Integral m is less than integral theta d. What's the meaning? Mx is the carrying capacity at each point x. So this is the total carrying capacity for the species capacity. This is the total population. The total population is always bigger than the total carrying capacity. The total carrying capacity should be an upper bound of the population, heuristically, right? However, for any d, I'm not talking about some d, no, for any d, the total population ended up bigger than that. And that is globally asymptotically stable. That is to say, as long as I allow them to move around randomly, whatever inertial value you give me, they end up, the same habitat ends up supporting bigger population than if the species don't move around. Is there a paradox here? Well, looks like it, there is one, but no. Simple proof, completely mathematical, completely rigorous. Just an equation by parts. Ecologists have noticed this long time ago. Mathematicians have. Just like, well, I don't want to say mathematicians have too, but later. Nowadays, of course, we know that. Just like the Turing's case, Turing first discovered this idea of activator-inhibitor thing using diffusion to model pattern formation. While when I was brought up in the 70s as a mathematician, I was brought up to believe that diffusion is a smoothing process, it's a trivializing process, something originally non-trivial. You add diffusion that trivializes. Anyway, coming back to this one, ecologists call this phenomena, call this theta d, they have an interesting name, dynamic equilibrium. Whatever that means, equilibrium. That is to say, if you allow the species to move, you get equilibrium that is bigger than the original. Than the population that was supposed to allow. Okay. Of course, you can think about it on your way home, driving or taking a bus, riding in the bus. Why? This fact has very interesting consequences when you come to Lotka-Volterra competition systems. And that's what I want to talk about next. Let me make sure I didn't leave out anything for the single equation. Very good that I checked. Okay. There is an interesting open problem. Actually, it's something puzzled me, or has puzzled me for a very long time, up to this day, and I don't know the solution. I don't know the solution. For this theta d, you can actually prove. This we will probably not prove here. I probably won't have time. Okay. You can prove this theta d. The theta d has the following property. I write it down here. The theta d goes to m pointwise or uniformly if d goes to 0. And the theta d goes to a constant m bar as d goes to infinity. So what is m bar? M bar is the average of m, of course. It's 1 over omega measure, integral omega. Yeah. it's a standard proof. If you're an expert, it's a standard proof. If you are not, it's a standard proof too. If you're interested in, you should figure that one out. All right, so what happens? Let's look at the integral theta d, the total population theta d. Theta d goes to m. As d goes to 0 or infinity. Doesn't matter which one. Right? So let's draw the picture. This is my d, diffusion coefficient rate, and this is my integral m. Then I'm going to plot the graph of integral theta d. That'll look like something like that. We know from this one, we know at 0, it's here. At infinity, it goes to the same constant. In between, it lies strictly above this line. But the shape we don't know. But in any case, there is a maximum, right? D positive. And the maximum is assumed somewhere. Question, where? And what is the maximum? Very little is known about this question. Where is D? Where is this maximum assumed? And what's the value? We don't know. It's a very simple question from here. So many young people here, what we need is an idea here, I suppose. So, okay. Let's move on to systems. I will describe another interesting phenomena of this Lotka-Volterra competition system. By the way, I do want to say that I'm going very slowly in my own feeling. I felt that I'm going slowly. Am I right? But anyway, if you think I'm too slow, let me know. I will go a little faster next time. I don't think I can go slower than this one. So. Because if I do, you won't learn much. But on the other hand, I also hate to, take off fast. Because if I lose you, then what's the purpose of this PDE school? I don't know. So I do want you to stay with me, but I feel that I'm going slowly. All right. So here's the Lotka-Volterra competition system. But so we have two competing species now, U and V. As I said, I will use the capital U and V to represent them. These are two competing species. I will assume these two species are completely identical. Except, of course, if they are identical, then there's nothing to deal with, except the dispersal rate. So let me write down the equation. Suppose I normalize everything, make everything simple. And this is the equation. Lotka-Volterra type, ut, I have d1 Laplacian u plus u. The carrying capacity, mx, non-constant, right? Minus u minus v. I have vt, v2, Laplacian v plus v, mx minus u minus v. Then I have so these two are identical, except D1 is different from D2. If D1 equals D2, they're identical. Right? Completely. So if D1 is different from D2, you see, this is the competition. This V here, the coefficient represents the competition rate of V versus U. It's 1, same as this one. Same thing here. The competition coefficient here is 1, same as this one. And they use the same resources at the same rate. So D1 is different from D2. So let's assume D1 is less than D2. Here I didn't write down the inertial value, so I should write it down. Sorry. So the initial value, ux0 equals u0 x, and the vx0 equals v0 x. And I have D1 is less than D2. So both the initial values are, of course, non-negative and not identically zero. This is non-negative and not identically zero. Because if one of them is identically zero, there's nothing to do. Right? The species stays zero all the time, of course. Now, here's a theorem. The theorem says, if D1 is less than D2, then no matter what U0, V0 are, U will always wipe out V. The solution U and V, independent of the initial value, always goes to theta D1, 0, as T goes to infinity. The theta D1 is the solution for the single equation. You see, if your V is 0, this is not there. This equation is the same as that one. So theta D1 is the unique steady state for the single equation U. Naturally, there's another solution, 0 theta D2. Right? I have two semi-trivial steady states. Theta D1 0 and 0 theta D2. It could be others in between. But the theorem says, if D1 is less than D2, number one, no anything in between. Nothing can lie in between. Number two, U wipes out V. Even at the beginning, U0 may be very small, V0 may be very large. Doesn't matter. Eventually, as T goes to infinity, V goes to 0. U goes to safety 1. This doesn't sound right. The slower diffuser wipes out the faster competitor. And this is a theorem discovered in 1998 by Dockery, Hudson, Mishaikov, and Peronowski. And this phenomena, we call it slower diffuser always prevails. And I'm going to prove that in the third lecture. The next lecture, I will do the single equation case, get you prepared, and then on the third lecture, I will prove the theorem in detail. the proof will be rigorous here. It's not that hard. We proved that. So slower diffuser always prevails in this case. Now, of course, the question is why? Mathematically, you find something, but how come that's the case? All right. To understand this thing, we're going to use two approaches. I mean, two different approaches. One is by, all right. One is from the diffusion, just diffusion side. What we're going to do is that we're going to put this result in a slightly bigger, slightly larger context. So this is Lotka-Volterra. Competition system. Ut is B1 Laplacian U plus U M1 x minus B1 U minus C1 V. Vt is D2 Laplacian V plus V M2x minus B2U minus C2V. And then I have Neumann, again, boundary. And initial value. Of course, we're going to look at the simplest case for the Lotka-Volterra computation system. We're going to use the simplest case for Lotka-Volterra computation system to approximate that thing. And this approach was proposed by Yuan Mo. And he had done some fundamental work in this direction. In particular, he related this fact. He related this one in his approach to understand this phenomena to the computation system. The slower diffuser must prevail. It's a very nice approach, very nice work. The second approach, I only have a few minutes, so I will not, because we're going to spend maybe more than one lecture on this one anyway. I wouldn't be able to finish it anyway, so maybe I will talk about that later. The second approach is a little bit different. Maybe I use that here. So I'm assuming I have about an hour. I'm using up my full hour. Sorry, not just 50 minutes. The second approach is due to, the second approach to understand this phenomena is due to, or rather not quite, but it's sort of extension, goes beyond this one, is due to Cantrell, Kostner, and Yuan Low. 3 of them. The single equation case started with, actually, with Kostner. But anyway. They say that suppose, let's say suppose you have 2 species competing. Here we are assuming both of them are done, right? They move randomly. So Kostner had an idea that suppose U is smart, or say smarter, you can detect where M is larger and move toward that. And that's what somebody said earlier, that what happens is this advection term. So this is what they did. They take the same, I think it's easier that I use this one. So I will erase this and make a little more room, okay? All right, maybe I don't erase anything. I use a different color. Okay. So Kendra, Kostner, and Yuan Low said the following. So this term, you can write it in the following form, right? It's divergence gradient d1, right? Same thing. If you write it in this form, shows that where the equation comes from, this is the flux, or the negative of the flux anyway. So they say if you can detect, if you're smarter, you can detect where M is larger and move toward M, then the first equation gets changed to this one minus alpha U gradient M. The extra term comes in. Gradient M tells us where U should be moving, which direction you should be moving. And alpha measures how strong you can sense that, how strong you should move in that direction. So we're going to replace this term by that. The rest stays the same. Of course, we need to change the no flux boundary condition to what? To D1 minus alpha. Sorry. So we also need to add another term here for the boundary condition, because this means no flux boundary condition. So what happens? Suppose your U is smaller, can detect where M is large and move toward M. What happens? Again, it's kind of interesting. If M is 0, let's say D1 is less than D2, right? It doesn't have to be much smaller. Just anything, just smaller than that by any small amount, U wipes out V if alpha is 0. What happens when alpha is large? It turns out V always survives. Not only V survives, V, or there are other assumptions. For instance, suppose M is nowhere constant, the gradient M is never 0, or the set is 0, the gradient equals 0, measure is 0. Then they show that is V, that is M actually moves. M actually is oscillating, is non-constant. Anyway, in any interval. Then they show that actually V is doing much better than U. Not just V survives, I should say. For any initial value, V survives. You can never wipe out V. And actually when alpha goes to infinity, V is the 1. The total population of V goes to roughly the steady state population, as if U doesn't exist. So that would be the last lecture that I would describe. What happens when you put this in, with this condition. So that's roughly what I'm going to talk about in this week. And are there any questions?